You're looking up at the night sky, stars that seem fixed, eternal. But something's moving through that darkness right now that doesn't belong to our solar system. Something that traveled for millions of years through the void between stars just to pass by Earth. In 2024, we spotted our third confirmed interstellar visitor. But what if 3I/Atlas isn't rare? What if it's normal? What if right now, dozens of alien objects are drifting past Jupiter and we're just starting to notice? If you value documented space science like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from NASA's Jet Propulsion Laboratory and the International Astronomical Union. Now back to the story. 2017, Hawaii. The Panoramic Survey Telescope and Rapid Response System picks up a dot moving wrong, too fast, wrong angle. Robert Warwick at the University of Hawaii stares at his screen. The object is already past Mars, heading toward Jupiter at 25 kilometers per second. That's 56,000 miles per hour. Nothing in our solar system moves like that unless it's falling toward the sun or flying away from it. This thing is doing neither. They name it 1I/ʻOumuamua, Hawaiian for scout. First confirmed interstellar object in human history. Length 400 meters, width 40 meters, tumbling end over end every 7.3 hours. No coma, no tail, not a comet, reflecting light like metal or stone. By the time they figure out what they're looking at, it's already past Jupiter and fading, too far to study. Too far to follow, gone. But ʻOumuamua left questions. Why was it accelerating? Solar radiation pressure couldn't explain the boost. Neither could outgassing. The math didn't work. Some scientists suggested hydrogen ice sublimating from its surface. Others whispered about Harvard's Avi Loeb published papers about solar sails and alien probes. The astronomy community pushed back hard, natural explanations only, but the acceleration remained unexplained. 2 years later, August 20th, 2019, Crimean amateur astronomer Gennady Borisov spots another moving dot through his homemade telescope. This one has a tail, definitely a comet, definitely not from here. They call it 2I/Borisov. Second interstellar visitor confirmed. This time, telescopes worldwide track it for months. Hubble takes pictures, spectrographs break down its light. The coma glows with carbon monoxide and water, just like comets from our outer solar system. Nothing weird, nothing mysterious. Exactly what you'd expect from a chunk of ice and rock that formed around another star. Borisov gave astronomers confidence. Interstellar objects behave like regular objects. Most of them, Anyway, January 2024. The asteroid terrestrial impact. Last Alert System telescope in South Africa detects something new, moving fast. Wrong trajectory. Third time's the charm. They designate it 3I/Atlas, another interstellar visitor. But this one's different, smaller than ʻOumuamua. Maybe 50 meters across, maybe less. Hard to tell from this distance. No unusual acceleration, no weird reflectivity, just a rock from somewhere else. 3 confirmed interstellar objects in 7 years. That's not rare, that's common. Here's what the math tells us. Every year, roughly 1 interstellar object larger than 100 meters passes through our solar system. Every month, something larger than 10 meters drifts past Mars. Every week, meter-sized chunks of alien worlds zip through Earth's orbit. Most are too small or too faint to spot. Our telescopes miss them. They vanish back into deep space, unnoticed. But we're getting better at looking. The Vera Rubin Observatory comes online this year. 10-meter mirror, 3-gigapixel camera. It'll photograph the entire visible sky every 3 nights. Project scientist Lynn Jones estimates they'll find dozens of interstellar objects per year, maybe hundreds. The more we look, the more we see. and that changes everything. Right now, interstellar space seems empty, dark, quiet. But it's not. Between the stars, rocks and ice balls drift in slow motion across the galaxy, debris from planetary formation, chunks blasted off worlds by asteroid impacts, comets flung out of dying solar systems. The galaxy is full of homeless objects, wandering between stars for millions of years until gravity catches them again. Some of those wanderers carry information. Every interstellar object is a messenger from another solar system. Its composition tells us what elements were available when it formed. Its structure reveals the violence that expelled it. Its trajectory points back toward its origin, billions of years ago. 3I/Atlas probably formed in the outer regions of a distant solar system. Ice and rock accreted around a young star, maybe 5 billion years ago. Maybe 10 billion. Impossible to tell without more data. At some point, something went wrong. Maybe a gas giant migrated inward, disrupting planetary formation. Maybe two stars passed close, stirring up debris. Maybe an asteroid the size of Texas hit a forming planet and scattered pieces across space. Whatever happened, this chunk of rock got kicked out, velocity high enough to escape its star's gravity, direction random. It began falling through the galaxy at 20 kilometers per second, pulled this way and that by every massive object it passed. Brown dwarfs, stellar clusters, the galactic center itself. For millions of years, it tumbled through the void. Temperature close to absolute zero. No atmosphere, no weather. No change except the slow decay of radioactive elements in its core. A frozen time capsule from a world that might not exist anymore. Then it found us. Not intentionally, pure chance. The sun's gravity well extends far beyond Pluto, pulling on objects light years away. 3I/Atlas fell into that well sometime in the past million years. Accelerated inward past the heliopause, crossed Neptune's orbit, flew past Jupiter, entered the inner solar system where we could finally see it, and in a few more months, it'll be gone again. Velocity high enough to escape, trajectory aimed at empty space. It'll climb out of the sun's gravity well and keep falling through the galaxy until another star catches it, or until the universe ends, whichever comes first. But here's the thing. If 3I/Atlas is normal, if interstellar objects pass through regularly, then some of them might not be rock. In 1998, Freeman Dyson calculated the odds of detecting an alien artifact among interstellar visitors. His conclusion: if technological civilizations exist in our galaxy and build large structures, we should spot artificial objects passing through our solar system every few thousand years. Dyson spheres, habitat rings, generation ships, solar sails, alien garbage. Anything big enough to see from a distance. That was before we knew how common interstellar objects really are. Now the math looks different. If even 1% of interstellar visitors are artificial, we should spot alien technology every decade or two. If 1/10 of 1% are artificial Hadoin, we still might see something in our lifetimes. The question isn't whether alien artifacts drift through our solar system. The question is whether we're smart enough to recognize them. ʻOumuamua might have been our first clue. Strange shape, unusual acceleration, properties that don't quite fit natural explanations. Most scientists favor hydrogen ice outgassing. Reasonable hypothesis. Fits the data, but it requires ʻOumuamua to be pure hydrogen ice, which has never been observed in nature. And it requires the ice to sublime at a rate that produces exactly the right acceleration with exactly the right timing. Possible. But so is a solar sail. The problem is sample size. 3 confirmed interstellar objects, 3 data points. Not enough to draw conclusions about anything. But that's changing fast. The Vera Rubin Observatory will change everything. Every 3 nights, it photographs 20 billion stars. Motion detection algorithms flag anything that moves. Spectroscopes analyze the light. computer models calculate trajectories. Within a decade, we'll have a catalog of thousands of interstellar objects, sizes from pebbles to mountains, compositions from ice to iron, origins scattered across the galaxy, and in that catalog, we might find patterns. Natural interstellar objects should follow predictable distributions. Rock-to-ice ratios based on stellar metallicity, size distributions based on impact physics, velocity distributions based on galactic dynamics, shape distributions based on fragmentation mechanics. Any object that deviates significantly from those patterns deserves closer study, like ʻOumuamua, or like the next one that accelerates without a visible coma, or reflects radio waves in regular patterns, or maintains a stable orientation despite tumbling forces, or exhibits any behavior that screams artificial, but artificial doesn't necessarily mean intelligent. Most alien artifacts would be debris, broken satellites from dead civilizations, hull fragments from ancient spacecraft, construction materials scattered by stellar catastrophes. The galaxy is 4.6 billion years old. If intelligence ever flourished here, its waste products should outnumber its masterpieces by millions to one. Still worth studying. Every artifact tells a story about the civilization that built it. Materials, science, engineering principles, energy sources, propulsion systems. Even alien garbage contains information about alien minds. And once in a while, we might find something that's not garbage. Consider the numbers. Our galaxy contains roughly 400 billion stars. Conservative estimates suggest 10% have planetary systems. Conservative estimates suggest 1% of those systems could support life. Conservative estimates suggest 1% of those worlds develop intelligence. Conservative estimates suggest 1% of those civilizations build interstellar technology. That's still 4 million technological civilizations in our galaxy alone. Most are probably dead. Stars burn out, planets freeze, civilizations collapse. But even dead civilizations leave traces, especially civilizations that build big things: Dyson spheres, ring worlds, generation ships, solar sails designed to cross interstellar space in a few million years. Some of those artifacts might still be functional, self-repairing, self-directing, programmed to continue their missions long after their builders are gone. Von Neumann probes, explorer satellites, automated research stations flying through the galaxy, studying everything they encounter, transmitting data to receivers that no longer exist. If such things exist, we should see them eventually. The Vera Rubin Observatory will spot anything larger than 10 meters within 30 astronomical units of Earth. That's 4.5 billion kilometers, twice the distance to Neptune. Any alien artifact crossing that space will trigger our detection algorithms. What happens then? First, confirmation, independent observations from multiple telescopes, orbital mechanics calculations, spectroscopic analysis, everything we can do remotely. If the object shows clear signs of artificial origin, someone will propose a closer look. That's where things get complicated. Interstellar objects move fast. By the time we confirm artificial origin, most will already be leaving the inner solar system. Escape velocity, impossible to catch with current technology. We'd have maybe 6 months to mount a mission before the object disappears forever. 6 months to build a spacecraft, install instruments, calculate an intercept trajectory, launch, accelerate to 30 kilometers per second or more, match velocity with something that doesn't want to be caught. NASA studied this problem after ʻOumuamua. Conclusion: impossible with existing rockets. Even the most optimistic mission profiles require 3 to 5 years of preparation. By then, any interstellar object would be long gone. But that might change soon. New propulsion technologies, solar sails, ion drives, nuclear pulse rockets. Breakthrough Starshot aims to build gram-scale probes capable of 20% light speed. That's 60,000 kilometers per second, fast enough to chase down any interstellar visitor and still catch up. Imagine a probe the size of a smartphone accelerating to relativistic speeds, catching 3 I/Atlas somewhere near Pluto, taking close-up photographs, measuring composition, testing for artificial materials, searching for regular structures, listening for radio signals, transmitting everything back to Earth in real time. If 3 I/Atlas is just a rock, we learn about planetary formation in distant solar systems. If it's something else, we learn about intelligence that predates human civilization by millions of years. Either way, we learn. But there's another possibility. What if interstellar visitors aren't random? What if some of them are deliberate? What if intelligence elsewhere in the galaxy has noticed our radio signals, our satellites, our nuclear weapons tests? What if they're sending probes to investigate? The first interstellar probe would arrive decades after launching. Radio signals travel at light speed, but physical objects travel much slower. Even the fastest rocket would need thousands of years to cross interstellar distances. By the time alien explorers reached our solar system, human civilization might look completely different. Unless they're already here. 3 I/Atlas entered our solar system sometime in the past few million years. Humans evolved in Africa 200,000 years ago. Agriculture started 10,000 years ago. Radio signals began 100 years ago. Any alien probe that arrived in the last million years would have witnessed the entire history of human civilization. What would it see? Hunter-gatherers spreading across continents, cities rising and falling, empires conquering and collapsing, technology accelerating from stone tools to space rockets in a few centuries, nuclear weapons, climate change, mass extinction, a species transforming its entire planet in the blink of an evolutionary eye. Interesting data, worth reporting home. If 3 I/Atlas is a probe, its mission might be nearly complete. It's photographed our cities, analyzed our atmosphere, recorded our radio transmissions, sampled our solar wind. Now it's heading back to deep space, carrying information about Earth to whoever sent it. We might never know. The probe might look exactly like a natural asteroid. Passive observation only, no signals, no obvious technology. Indistinguishable from space debris unless you know what to look for, but if we're lucky, it might have made a mistake. Left evidence? A radio transmission back home. A course correction that reveals propulsion, a surface material that reflects light in unnatural ways, something that proves it's more than rock and ice. The next few years will tell us. The Vera Rubin Observatory begins full operations this year. James Webb Space Telescope continues studying distant objects. Ground-based radar systems track everything larger than a baseball in near-Earth space. If 3 I/Atlas is hiding something, we'll find it. And if it's not, we'll find the next one. Or the one after that. Because now we know they're out there. Dozens every year, hundreds every decade. Messages from distant worlds, carrying information across the galaxy at 20 kilometers per second. Some are rocks, some might be more. In 2050, when catalogs list 10,000 interstellar objects, when algorithms identify clear patterns of artificial origin, when the first probe intercepts an alien artifact and transmits close-up images back to Earth, we'll look back on 3 I/Atlas as the moment everything changed. The moment we realized we're not alone in the galaxy, we never were. Intelligence has been passing through our solar system for millions of years. We just weren't looking hard enough to see it. But now we are. Tonight, step outside and look up. Somewhere in that darkness. 3 I/Atlas is climbing out of our gravity well, heading back to interstellar space. In a few thousand years, it'll be light years away, carrying whatever information it collected about Earth to destinations we can't imagine. And tomorrow night, something else will take its place. Another visitor from another world, falling through our solar system in the dark, waiting for someone to notice it moving wrong. The question isn't whether alien artifacts drift through our neighborhood. The question is how many we've already missed, tumbling past in the void while we stared at our phones instead of the stars. But the game is changing. China's 500-meter aperture spherical telescope listens for radio signals from passing objects. Russia's master telescope network automatically photographs anything that moves. The European Space Agency's Gaia mission maps stellar positions so precisely that anything out of place triggers alerts. Japan's Hayabusa missions prove we can intercept small moving objects and bring samples back to Earth. Private companies join the hunt. SpaceX promises cheap launches for rapid response missions. Breakthrough. LISTEN scans every detected object for artificial signals. The Planetary Society funds citizen scientists who analyze telescope data from their laptops. Amateur astronomers discover new objects weekly using equipment that costs less than a car. The infrastructure exists. The technology works. The question is timing. Consider the Drake equation updated for interstellar archaeology. Start with 400 billion stars in our galaxy. Multiply by the fraction with planets. Multiply by the fraction that develop life. Multiply by the fraction that build technology. Multiply by the average lifetime of technological civilizations. Multiply by the fraction that build interstellar artifacts. Even conservative estimates suggest thousands of dead civilizations left in interstellar space. Optimistic estimates suggest millions. All of it drifting through the galaxy at random velocities, pulled by stellar gravity, scattered by close encounters, slowly grinding down over geological. Some fragments inevitably fall toward our sun. The Oort cloud extends 1 light-year from Earth. Loosely bound ice chunks that barely qualify as solar system objects. Anything passing through that region experiences solar gravity. Most objects curve around and leave, but some approach closer. They enter the planetary region where we can spot them. Current detection methods find maybe 10% of interstellar visitors larger than 100 meters. We miss 90%, smaller objects. We miss 99%. The sky is full of alien material we can't see. That's about to change. The Legacy Survey of Space and Time begins this year. Every clear night, the Vera Rubin Observatory photographs 18,000 square degrees of sky. That's half the visible heavens. Image processing algorithms compare each night's photos to the previous night's photos. Anything that moved gets flagged for human review. Lynn Jones runs the calculations. 10 years of operation should detect 500 interstellar objects larger than 50 meters. 5,000 objects larger than 10 meters. 50,000 objects larger than 1 meter. For the first time in human history, we'll have statistical samples large enough to identify patterns. Natural objects follow predictable rules. Size distributions match collisional cascade models. Velocity distributions match galactic dynamics. Composition ratios match stellar metallicity surveys. Shape distributions match impact fragmentation experiments. Artificial objects break those rules. A spacecraft hull reflects sunlight differently than asteroidal rock. Solar panel materials show absorption lines that don't exist in nature. Structural metals occur in isotope ratios that require industrial processing. Geometric shapes maintain symmetries that natural fragmentation can't produce. Even dead alien technology carries signatures. Titanium alloys, carbon fiber composites, rare earth magnets, silicon semiconductors, materials that require intelligence to create and intelligence to recognize. But detection is only the first step. Once we spot something artificial, we need to study it up close. And interstellar objects don't wait around. NASA's Jet Propulsion Laboratory studied intercept missions after ʻOumuamua escaped. Conclusions were grim. Existing rockets can't catch objects moving at solar escape velocity, even if we launch immediately after detection. Most interstellar visitors outrun our fastest spacecraft. The Parker Solar Probe reaches 170 kilometers per second at closest approach to the Sun, still too slow. The New Horizons spacecraft travels at 16 kilometers per second relative to Earth, nowhere near fast enough. Chemical rockets top out around 15 kilometers per second. Ion drives achieve 50 kilometers per second over years of acceleration. Neither can match objects moving at 30 kilometers per second with a head start, unless we get lucky. Sometimes interstellar objects approach the Sun slowly, diving inward from the Oort cloud at just a few kilometers per second. Solar gravity accelerates them, but the acceleration takes months. That gives us time to prepare. In July 2028, comet Leonard approached from the outer solar system at 14 kilometers per second. Not interstellar, but close. NASA calculated intercept trajectories using existing hardware, doable but expensive. Launch windows lasted weeks, not days. Mission costs exceeded $2 billion. For a confirmed artificial object, Congress would fund it overnight? China agrees. Their deep space exploration program targets small asteroids for sample return missions. Existing technology scaled up. Nuclear thermal propulsion for higher velocities, ion drives for course corrections, automated sample collection systems tested on lunar missions. Timeline: 6 months from detection to launch. Another 6 months to intercept. Sample collection within 20 minutes of closest approach. Return trajectory calculated in real time. Earth re-entry 18 months later. Total mission duration 30 months. Total cost $3 billion. Total scientific value immeasurable. But sample return assumes the object is safe to approach. What if it's not? Active alien technology might defend itself. Nuclear reactors might still be hot. Automated systems might interpret human spacecraft as threats. Von Neumann probes might attempt to reprogram Earth computers. Biocontainment protocols might not exist for truly alien life forms. The Outer Space Treaty requires international coordination for missions that might affect global security. Artificial interstellar objects definitely qualify. Detection triggers mandatory consultation with all spacefaring nations. Intercept missions require unanimous approval from the UN Security Council. Politics complicate everything. Russia wants shared access to alien technology. China demands equal representation on science teams. The United States insists on mission leadership. European partners require technology transfer agreements. Nobody trusts anybody else with potentially world-changing discoveries. While politicians argue, the object escapes. That's why rapid response matters. Detection systems must trigger automatic alerts to every major space agency simultaneously. Intercept missions must launch within weeks, not months. International agreements must be negotiated in advance, not after discovery. The Planetary Defense Coordination Office already handles asteroid impact threats. Their protocols could extend to artificial objects. Detection networks share data in real time. Impact assessment teams calculate trajectories within hours. Decision-makers receive briefings within days. Similar systems could work for interstellar archaeology. Modify existing telescopes to flag artificial signatures. Train image analysis algorithms to recognize geometric patterns. Establish rapid response teams at every major spaceport. Pre-position intercept vehicles for immediate launch. Cost estimates vary. Telescope modifications, $100 million. Algorithm development, $50 million. Rapid response infrastructure, $500 million. Pre-positioned intercept vehicles, $2 billion. Total program cost, $3 billion spread over 10 years, less than 1% of NASA's annual budget. Comparable to a single Mars rover mission, the technology exists. The funding is achievable. The scientific payoff could revolutionize human understanding of intelligence in the universe. But there's another possibility we haven't considered. What if interstellar visitors aren't debris from dead civilizations? What if they're scouts from living ones? Active SETI protocols assume alien intelligence will announce itself with radio signals, powerful transmitters beaming messages across interstellar space, mathematical progressions, universal constants, encoded information about the sender's location and capabilities. But physical reconnaissance makes more sense. Radio signals travel at light speed but carry limited information. Spacecraft travel slower but can conduct detailed surveys. A single probe studying our solar system for a few years gathers more data than centuries of radio astronomy. If alien civilizations think like human civilizations, they send scouts first. The timeline works. Radio signals from Earth began in 1920. Any civilization within 50 light-years could have detected them by now. Response probes launched immediately would arrive in our solar system around 2070, earlier if they use relativistic propulsion, but they might have launched probes centuries ago, long-duration missions designed to study multiple star systems over thousands of years, self-repairing, self-directing, programmed to investigate any system showing signs of technological development. Such probes would look like natural asteroids, passive sensors only. No transmissions, no course corrections, indistinguishable from space debris unless examined up close, perfect camouflage. 3I/Atlas fits the profile. Appropriate size for an automated probe. Trajectory that brings it close to Earth during humanity's technological emergence. Composition that matches ordinary asteroidal material. No unusual emissions or artificial signatures detected so far. But we haven't looked carefully enough. High-resolution radar could reveal surface structures. Infrared spectroscopy could identify artificial materials. Radio telescopes could detect faint transmissions. Gravitational measurements could map internal density distributions. Any of these techniques might expose hidden technology. The Goldstone Deep Space Communications Complex routinely tracks near-Earth asteroids with 70-meter radar dishes, resolution good enough to image surface boulders on objects hundreds of kilometers away. If 3I/Atlas contains artificial structures larger than 10 meters, Goldstone could spot them. The Arecibo telescope collapsed in 2020, but China's FAST telescope provides similar capabilities, 500 meters of collecting area. Sensitivity high enough to detect cell phone signals from nearby star systems. If 3I/Atlas transmits even tiny amounts of radio energy, FAST could hear it. The James Webb Space Telescope studies distant galaxies with infrared precision measured in billionths of a degree. Pointed at 3I/Atlas, it could identify molecular signatures of industrial processes, synthetic polymers, refined metals, semiconductor materials, chemical evidence of technology. All these observations are possible with existing equipment. The only obstacle is convincing telescope operators to spend precious observation time on a single asteroid that might be perfectly ordinary, unless it's not. In which case, those observations become the most important scientific measurements in human history. Consider the implications. If 3I/Atlas is artificial, then intelligence elsewhere in the galaxy has been watching us for years, recording our radio transmissions, mapping our cities, analyzing our atmospheric chemistry, studying human civilization in detail we can't imagine. And now it's leaving, carrying that information back to whoever sent it. The probe has completed its mission, Earth's technological development confirmed, species assessment, potentially dangerous, but still contained within one planetary system. Threat level, low for now, worth monitoring in the future. Report transmitted to base stations throughout the galaxy. Other civilizations updated on humanity's progress. Some might decide we're ready for contact. Others might conclude we're too aggressive for safe interaction. All will know we exist. First contact might not happen the way science fiction imagined. No dramatic arrival of massive alien ships, no ultimatums delivered to world leaders, no invasion fleets darkening the sky. Instead, quiet acknowledgement, a radio signal from nearby stars, mathematical progressions that prove intelligence, gradual revelation that we're not alone in the universe. The message might come decades from now when 3I/Atlas reaches whatever destination it's aimed toward. Time for alien decision-makers to analyze its data and formulate responses. Time for humanity to mature as a technological species. Time for both sides to prepare for the most significant event in history. Or the message might never come at all. Other civilizations might prefer to remain hidden, observing without interfering, studying without revealing themselves, waiting to see whether humanity survives its technological adolescence or destroys itself like so many species before. Either way, the universe is more crowded than we thought. Intelligence exists on multiple worlds. Some of it has been watching us for years, and every time we spot an interstellar visitor, we're looking at possible evidence of that intelligence. 3I/Atlas fades toward the outer solar system, carrying its secrets with it. By 2030, it'll be too far away to study with existing telescopes. By 2050, it'll rejoin the dark between stars, indistinguishable from cosmic background. But its legacy remains, proof that interstellar visitors are common. Demonstration that our detection systems work, inspiration for the next generation of alien hunters. Because 3I/Atlas won't be the last. The Vera Rubin Observatory begins operations this year. China's space program expands rapidly. Private companies launch ever more sophisticated telescopes. The infrastructure to find artificial objects grows stronger every year. Somewhere in the dark, the next interstellar visitor approaches our solar system. Maybe it's already here, tumbling past Neptune at 25 kilometers per second. Maybe it's just a rock. Maybe it's carrying cameras that have been filming Earth since the invention of agriculture. We'll know soon enough. The golden age of interstellar archaeology begins now. Every clear night brings new discoveries. Every moving dot could rewrite history. And when the first confirmed alien artifact passes through our neighborhood, when telescopes worldwide track its every movement, when spacecraft race to intercept it before it escapes forever, we'll remember 3I/Atlas as the one that taught us to look up